Hello and welcome to this lecture. We've been looking at integration for the past few lectures, and we saw some methods for integration, not really methods, some formulae for integration like polynomials, power, exponential and all that. All of that worked out in quite an easy way. But then when you have product of two functions, can you find the antiderivative easily is a question that comes up. So it turns out for all products, it may not be very easy. In some forms may not be very easy. The composition rules that we had for differentiation, the product rule we had for differentiation, the quotient rule we had for differentiation, such rules don't exist for antiderivative. You have to look at the thing and know whether it will work or not. Okay. So the next two methods we're going to discuss are two methods for dealing with products. When you have products of functions or even other forms, how do you approach that? Or what are the cases in which you can successfully do it? The first one is integration by substitution. It's a very powerful method. Many unlikely integrals that look like unlikely to have an antiderivative, some functional form, you may think this may not have an antiderivative. If you use substitution, you may get an antiderivative. Okay, so that's the nice idea about this. Basic idea is the following. Supposing you look at a function capital F, right, capital F of x, which is v of u of x. Okay, so this is a composition, right? You have a function u of x inside, and then there's a function v of x also. Okay, so I think we have seen this long ago. I just want to repeat that. So supposing you have a function like say e power x squared, right? So I can see it as u of x being x squared, and then v of x being e power x, and then this function is v of u of x, okay, which is v of x squared, and that is e power x squared. So this is called composition. You have one function inside and the whole function outside, and then you're composing the two functions. So this is composition. Whenever you have a composition like that, there is a very simple derivative rule. What is the derivative of v of u of x? It's, if you differentiate this, notice what I've done here in the proof. If you differentiate this f, v prime of u of x times u prime of x, that is f, isn't it? This is the thing. So you take v prime of x, instead of x you put in u of x, and then multiply it with u prime of x. Okay, so that is the way in which you do this derivative for compositions. Okay, so if you go back here, if you look at my composition here, my v prime of x is e power x, u prime of x is 2x, and what will be v of u of x the whole prime, the derivative of this composition, this will be v prime of u of x times u prime of x. So what is this v prime of u of x? This function e power x, I am going to put, instead of x I have to put u of x. So it will be e power u of x times u prime of x is 2x. Okay, what is u of x now? X squared. So it is e power x squared times 2x. You can also write it as 2x e power x squared. Okay, so that is v of x, u of x prime. So as in, this is what? This is e power x squared whole prime. Okay, there are many formulae like this. Like for instance, if you have square root of 1 minus x squared, this is a very common function. U of x is 1 minus x squared. V of x is square root of x. Okay, and you see here clearly v of u of x. I'll write it a bit quicker, is square root of 1 minus x squared. So in v of x, wherever you have x, you have to put u of x, which is 1 minus x squared. So square root of, instead of x, I'll put 1 minus x squared. Okay, so what will be v prime, v of u of x, the whole prime, the derivative, it's v prime of u of x times u prime of x, isn't it? So now what is v prime of x? It's 1 by 2 root x, but instead of x I have to put u of x, so it's x squared times u prime of x, which is minus 2x. Okay, so you see quickly that this is minus x, 2 and 2 will cancel by square root of 1 minus x squared. So this is a familiar composition rule for differentiation, to give you a couple of simple examples. Okay, so so if you have small f of x which is of this form, v prime of u of x times u prime of x, then capital F of x is simply the composition v of u of x. Okay, so this is the composition rule. Notice here I have found an antiderivative for a specific type of product. See, this is a product of v prime of u of x and u prime of x. for a product of two functions, I have found an antiderivative using the composition rule. But this is not a general product of any two functions. It is a product of this form. It needs to be v prime of u of x times u prime of x. Okay, so we will see a slight different way of writing it in the next slide, but this one is a important thing to do. Okay, so how do we use this? I will show you by example. This examples will sort of illustrate this key thing of identifying u and u prime inside an integral. Okay, or for finding an antiderivative inside a function. How do you identify u and u prime? What is the u and u prime hidden inside it? So this is a very important trick or a problem solving step with respect to finding antiderivatives and integration. Given a function form, can you identify a u prime? Can you identify a u which is interesting inside it? Okay, and then is there a u prime that's going to come from there in some form? Okay, so I'll give you a couple of examples. This example we just saw a little while ago. It's 2x times e power x squared. So when you look at this function, you should quickly see that this x squared is there and 2x is there, right? So notice this x square and 2x. X square, if you differentiate it, you get 2x, x square and x, right? So your eye should immediately go to this kind of a combination. Okay, so this takes a lot of practice. You have to see very many situations like this. So in general, when you have a composition like this, when you have e power x squared, you can look to identify u being that x squared. Okay, and then u prime, luckily in this case, it's out this side. Okay, so once you identify u prime, v prime, you're done. Right, so everything is the same. So f of x we have identified as e power u of x times u prime of x, where u of x is x squared and v prime of x is e power x. Remember, it's f of x is v prime of u of x times u prime of x. So whatever you have here, this function e power x is actually v prime of x, right? So it's v prime of u of x times u prime of x. And then you find an antiderivative for this. So this product should be such that you can find the antiderivative for v prime easily. Okay, e power x, I know what v of x is, right? So antiderivative here is very easy. So v prime of x is e power x, v of x is e power x. And then once you do this, the antiderivative for f is just e power u of x, right? So v of u of x plus c, we'll add the c, so you get e power x square plus c. Okay, so going from e power x square to 2x e power x square for many people is easy. But when you have to go from 2x e power x square back to e power x square, right, as an antiderivative, you have to identify these things. Okay, so that's important. So now we are able to find antiderivative of product of two functions, but only when they are in this special form. Here is one more illustration. 2x divided by 1 plus x squared whole square. If you have to differentiate it, you will use the quotient rule, there's no problem. But I want to integrate, I want to find the antiderivative, right? So in that case, you have 2x by 1 plus x square whole squared. And let me see, I mean, take your time, just try to think about it. You can pause the video here and think about if you can identify the u prime combo here. Okay. So continuing, you see that 1 plus x squared is here and 2x is here. So immediately your eye should jump to this 1 plus x squared as u, and then its derivative 2x being right there. Okay. So it's 1 by u of x squared times u prime of x, where u of x is 1 plus x squared. So I think first it starts with this u of x being 1 plus x squared. That's the first thing you identify. Okay, identify the u first. U of x is 1 plus x squared, and then you will see that u prime, is right there. So it becomes u prime multiplying 1 by u of x squared. Okay, so it starts with this identification of u of x. What substitution you can make? What is the u you can identify from this function? That's how integration works. Okay, so v prime of x in this case is 1 by x squared, right? So this 1 by u of x squared, it's 1 by x squared is the v prime. So this function, interestingly, is something that I can find an antiderivative for. This is just x power minus 2, right? X power minus 2 is, x power n is what? X power n plus 1, or x power a, when a is not minus 1, is x power a plus 1 by a plus 1, right? So it will be x power minus 2 plus 1 divided by minus 2 plus 1, and that's minus 1 by x. Okay. So once you have this, the remaining step is very easy. It's minus 1 by u of x minus 1 by 1 plus x squared. Okay. So notice once again, I want to remind you, if I given minus 1 by 1 plus x squared, going from there to here is a simple composition rule. On the other hand, if you are given 2x by 1 plus x square whole square, going this side, you have to identify this u of x, and then notice that this 2x is u prime of x. Okay. So this kind of identification, you will become better at it only when you solve problems on your own. Okay. So, you might see me do it 200 times, but that does not give you any ability to do a new problem on your own. To do a new problem on your own, you should fight with these kind of things, try to identify, and then eventually you will become much better at it. Okay, do try. Okay, so this same composition rule goes by the name of integration by substitution. So, here is where the idea comes from. You may have a function integration of this form, integral a to b g of u of x times u prime of x dx. Okay. So, notice what is going on here. There is this u of x which is prominently appearing and its derivative is also appearing. U of x should appear, its derivative should appear. Okay. So, even if the derivative does not appear, whenever you have a u of x like this, right, the g of u of x. So, you see here this ag of u of x. Okay. So, ag is what? Ag is the antiderivative of g alone. Okay. So, g of x is a function. Okay. I have here g of u of x, but instead of u of x, you can think of g of x itself as a function, right, just g of x. G of x is a function, its antiderivative is ag. Okay. If you compose u of x and ag, as in you put ag of u of x, then that becomes an antiderivative of this guy. It's again from the composition rule, it's exactly like that, right. Ag of u of x, if I do a whole derivative, it is ag prime of u of x times u prime of x. What is ag prime of u of x? It's g of u of x. That's the definition of the antiderivative, right. So, you get g of u of x times u prime of x. Okay. So, this is an important idea. Okay. So, once you know the antiderivative of this whole thing, you can use the fundamental theorem of calculus, right. So, how does the fundamental theorem of calculus work? Integral x equals a to b g of u of x u prime of x is ag of u of b minus ag of u of a. Why? Because this whole antiderivative is ag of u of x. So, what does fundamental theorem of calculus tell you? Antiderivative evaluated at x equals b, that is this guy, right, antiderivative evaluated at x equals b, minus the antiderivative of this guy evaluated at x equals a, and that is ag of u of a. That is it. So, the difference of these two is what this integral is. Now, this integral you can also write, you can also get this difference of antiderivatives in another way. What is this other way in which you can get? That is this right hand side integral. Okay. So, I am coming to this quantity both from the left hand side and from the right hand side. Okay, read it like that. From the left hand side I could come, you can also come to this quantity in another way. Okay, how do you do this? You look at the integral of g of y dy. Okay, g of y dy. It's not g of u of x u prime of x dx. It's just g of y dy. Right? You just look at g of y dy. This is very important. But I am now going to integrate from u of a to u of b, not a to b, but u of a to u of b. If you do that also, you get the same form. Do you agree? Right? If you do this, what is the antiderivative of g? It is ag. So, antiderivative of g evaluated at u of b is ag of u of b minus ag of u of a. Okay? So, this is the idea behind doing substitution. Okay? So, what people think of this as is substitution or change of variable. In this integration on the left here, I am going to put a new variable y to be equal to u of x. Okay. So, this is the core of the substitution idea. In your integrand, in your integral function, the function that you have to integrate, you notice that there is some u of x buried inside. Okay. A very good idea to always try is, try and substitute y equals u of x, okay, and see what happens. The next thing which is very interesting in this notation is, you identify a dy as u prime of x dx. Okay. So, a dy is sort of a differential in y. If y is u of x, if you do a small differential in y, it is the derivative of u times the small differential in x, right. So, that is the idea behind the derivative, isn't it. So, you go by a small distance in x, how much will you go by y? The slope is u prime, isn't it. So, if y is u of x, dy will be u prime of x times dx. So, this is the differential idea that we have seen long ago. So, u prime of x dx you can replace by dy, and u of x you can replace by y. Okay. So, this by substitution will go to this. But what happens to the limit x equals a corresponds to what in y? Y equals u of a, isn't it? If x is a, y is u of a. So, in the limit the limit will also change. It becomes y equals u of a to u of b. Okay. X is b, y becomes u of b because y is u of x. So, this is called changing variables inside an integral. Okay. This is different from simply changing the dummy variable. Okay, if I change the dummy variable, that's something else, right? Here I am saying y equals u of x. This variable y is related to x through this function u. U could be x squared, u could be 1 by 1 plus x squared or something, any function you like, right? So when I make that substitution, a lot of things change in the integral. How do they change? First of all, every u of x you have will become y. Okay, so like this g of u of x become g of y. What about dx? How will the dx change? It changes like this. When y is du of x, a lot of people think it as differentiate both sides. So when you differentiate y, you get like a differential dy and you get u prime of x times dx. Another way in which people think of this is dy by dx is u prime of x and you multiply dx to the other side. These are slightly dangerous notions, but if you understand them, it will work well. So dy is u prime of x dx. Okay. So when you have u prime of x dx, you can substitute it as dy, or you can say dx you can substitute as dy by u prime of x. Okay. So you put that in there, this u prime will cancel and you will get just dy. Okay. So notice how by this change of variables, you get from this form to this form, g of y dy. Once you do that, you also have to change the limit, right? This entire integral is in terms of x. I am moving to another variable y here. Okay, when I do that, I have to change my x limit from a to b to y limits, which is u of a to u of b. So I know this is a little bit of a lot going on, but this is the core crux of the idea. It's very, very powerful idea in finding antiderivatives and evaluating definite integrals. Okay, so I hope you saw this. It's like a change of variable. Instead of integrating from x a to b f of x, some complicated looking f of x, I am able to go to another variable y with through this transformation y equals u of x, and then suddenly it becomes just one function g of y dy because of this u prime occurring conveniently here. Okay, we are going to use it like this. This is the way in which this composition rule or substitution rule is used, but generally the substitution is very, very powerful if you execute it like this. Okay, so let's see a few problems. Here are a few problems where you can use the substitution rule to your advantage. Okay, so here is let me just go through some of these problems in some detail. So the first problem says 1 plus x plus 3 plus 2x. Okay, so 1 plus x by 3 plus 2x plus x squared the whole power 5, right. This is the function that you are looking at. Anytime you look at a function, the most obvious u of x in this, right, what is the u of x that's buried inside? It's 3 plus 2x plus x squared, isn't it? Right, do you see that? And what is u prime of x? So immediately you have to compute u prime of x. It is 2 plus 2x, isn't it? And now that is 2 times 1 plus x. Okay, so notice you got the 1 plus x also. So this function is nothing but u prime of x divided by 2 divided by u of x power 5. Okay, so you can rewrite it as 1 by 2 u of x power 5 times u prime of x. So now you have your simple looking type formula. You have a u prime of x here and a u of x power 5 here divided by 2 here, and you can use the composition and all of those things. So you identify that this is what? This is g of I think v of x being 1 by 2 x power 5, right. So this becomes v prime of x, isn't it? So let me just make sure I get that right. So if you want to go find antiderivatives, I think it's better to find the definite, it's the antiderivative. So it's better to find the definite integral. It's much simpler in the substitution. But anyway, v prime is this. So it's v prime of u of x times u prime of x. Okay. So once you have in this form, you have to find v of x. This gives you v of x is half will be the same, x power minus 5, right. So x power minus 5 will be x power minus 4 by minus 4. So you have here minus 1 by 8 x power 4. So that's v of x. Okay. So if you have f of x being this guy, the antiderivative of x is going to be v of u of x, and that is minus 1 by 8. Instead of x, I am going to put 3 plus 2x plus x squared raised to the power 5. Okay, raised to the power 4, I am sorry. That is the, okay, plus a c, we will add a plus c, should not forget that. Okay, I hope you saw the steps. So, first step is to guess a u of x. Okay, how do you guess a u of x? Notice what is inside some complicated looking term inside your function. This comes from practice. So, you notice a u of x, and once you do that, you identify a u prime and you get the same shape for the whole thing. Okay. So, let me look at the other function here. So, notice here this x minus 1 e power minus x minus 1 whole squared. What is going to be a u of x? Okay, take a pause here, think about the u of x, I will give you the answer shortly. Continuing, the answer will be u of x equals x minus 1 whole square. Okay, so you can notice that that is the part that is here, and then if you take a u prime, you will see you get a x minus 1, and then your v prime will be e power minus x, and then from there you can proceed. Okay, what about this one, x squared e power 1 plus x cubed? What is the most obvious u of x that is staring at you in this? 1 plus x cube. Okay, so try that, try these problems, and these two problems you try on your own, 4 and 5. Okay, so I hope you see these easy problems where you have to identify this u of x, and u of x is like the term or expression which is inside some other power, like for instance here it's 1 plus x power 20, like that, right. So how do you identify the u of x here? You will see. Okay, so I hope this is easy for you. I showed you two examples and I walked you through some of them. I'm not going to do everything in detail. That doesn't really help you. Let me tell you that once again. You have to look at it and try your best. Okay. So let's look at the definite integrals here. Many of them are reasonable. You know, e power minus x is very reasonable. You know how to do that. 1 minus 2x power 3. What is the u of x you're going to do? Let me start with that substitution. I think the substitution is very interesting. So let me just do that. Integral 0 to 1 minus 2x whole power 3 dx. Okay. So here the most obvious substitution you are looking at is to do y equals 1 minus 2x, right. So that is the u of x here. Okay. So if you do the substitution, you get dy is, you have to differentiate this. If you differentiate, you get minus 2 dx. Okay. So or this another way to write it is dx is dy by minus 2. Okay. And then what about the limits under this substitution? 0 goes to 1 minus 2 into 0, 1. 1 goes to 1 minus 2 into 1, which is minus 1. So this will become, under this substitution, integral, instead of 0 minus 1, instead of 0 it's 1, instead of 1 it's minus 1. 1 minus 2x is y, right. So y cubed, dx is dy by minus 2. Notice how easy this is. This is a very simple textbook procedure. Many of you might have seen it in school. If you have not, this is a good way to pick it up. So minus 1 by 2 integral 1 to minus 1 y cube dy. So here notice this 1 to minus 1, it comes off because of the way in which we did the substitution, but there is a minus here luckily. But even if the minus is not there, how do I get rid of 1 to minus 1? Make it as minus integral minus 1 to 1. So this minus and minus will cancel, so it will just become minus 1 to 1 y cube dy. Okay. What is integral minus 1 to 1 y cube dy? This will end up being 0, right. How do I know it's 0? Because this is an odd function. Okay, and you can also do it the other way. If you don't believe me, you can do, you know, y power 4 by 4, evaluate between minus 1 and 1 and you'll get 0. Okay, so this becomes 0. Okay, so it's a very easy evaluation that we did here. Okay, so the third problem, if you look at it very carefully, what is the substitution you will make here? For the third problem, integral 1 to 2 e power minus 1 by x squared dx. What is the substitution that you are looking at? If you want, you pause the video here and think about it, but otherwise it will be y equals 1 by x, isn't it? So you do y equals 1 by x, and then you will say dy will have minus 1 by x squared times dx. You notice that by x square is showing up magically here. I have cooked up a problem like that, and then you change the limits, change the dx, you will get your answer. Okay, try that. What about this one? Integral 0 to 5 z root z square plus 1. What is the y? What is the substitution? The dummy variable is changed. It doesn't mean anything. What is the substitution here? You notice here, you can pause and come back to it after I give you the answer. The substitution will be z square plus 1, isn't it? Y equals z square plus 1, and then you can go through the same steps that I showed you, and this will work out very, very nicely. Okay. What about this one? Let me do this one. This one is slightly different from what you have seen. Z root z plus 1. Okay. So, integral, I think it's 0 to 5, isn't it? 0 to 5, anything else also is okay. Z root z plus 1 dz. Okay. So, once again, the most obvious thing that you are looking at is y equals z plus 1, isn't it? It's very clear, and dy becomes just dz, right, because the derivative of this is just 1. So, it's just dc, or dz is dy, that's the same. And what about the limits? 0 go to 1, 0 goes to 1, 5 goes to 6, right. So, if you do this, you are going to get 0 to 5. What is z now? See, you have to, instead of z, you have to put y minus 1, right. So, you put instead of z, you put y minus 1, right. So, that is the change of variables that you have to do here, okay. Instead of z, you put y minus 1. So, this is also an important part to look at. So, this thing you can invert it and make z equals y minus 1. So, if you put that here, I am going to get y minus 1 multiplied by square root of y. Notice that z plus 1 became y, square root of y dy, okay. The limits have to be changed, I apologize for that, it should go from 1 to 6, okay. So, how do I do y minus y into root y? Do not be too confused by it, this you can just multiply out, y into root y. What is y into root y? Y power 3 by 2 minus y power 1 by 2 dy, and this you can do, right. Y power 3 by 2, it's you know the antiderivative of this, right. So, this is y power 5 by 2 by 5 by 2 minus y power 3 by 2 by 3 by 2 between 1 and 6. Can evaluate this, just numerical evaluation after this point. Okay. I hope you saw how I did this. So, the key to this whole thing is the substitution, y equals z plus 1, and the z plus 1 you just identify from this form, you know, this is the standard thing that everybody does. Okay. So, here also is another form, I will leave this as an exercise for you. Something is staring at you here for the substitution, you can make that and it will work out very easily. Okay. So, thank you very much. I hope you saw this substitution as an idea that is very important in simplifying your calculation of integration. There can be more complicated things like this, and but this concludes the lecture at this point. Thank you.